Hey everybody, sorry about that. Thing one had something in her eye, and then I, looked into her eye to try to find it. And then she blinked and was like, nah, I think it's gone. Right then. How's everybody doing? I had a lovely vacation. Well, it wasn't really a vacation, but a lovely time away. Went and saw my parents, grandparents, aunts and uncles. It was an unfortunate, event that brought us all together, but at the same time, it was nice seeing everybody. So, we've got 2 orders of business tonight. One is The Mathematics of Space Exploration by Merle H. Arendt. We did sort of a treatise on the first chapter, and we were working on some of our questions that were in it, and that were in the first section of the first chapter. And I thought I'd go through some of those. I don't remember where we left off, so we'll just go over them again, probably. That's fine. I also wrote teaching notes for that first section, which I definitely did not do last time. I think I just read it. Hey, walking stick. Yes, that is true. So over on Zach's stream, we always kind of hang out like on each other's streams all the time, as much as we can, when we're not doing something else. If anyone does want to see the stream that was basically a treatise of like what these guys wanted to do, I was telling them last time. I was over on Dawn's channel. Dawn Does Math. I was like, yeah, I probably should have actually watched that. Search Dawn Does Math. Math. We want your input. Math streamer community discussion.
Alright, everyone. This video is a little bit different.
That one. So if anyone is interested in watching this, this is basically the guys who got together in November and started talking about like what we want to do as a community. This was actually before I met any of them, I think, or maybe I had just met them. They were coming over and hanging out on my stream, and I didn't know who any of them were. Didn't know that any of them streamed. I think they were kind of checking me out to see how I was, and it was shortly after that in December when I was like hanging out on their streams all the time. So that is kind of, again, the treatise of what they were planning on doing. By all means, if anybody wants to watch that, go ahead, but it's a long discussion. Let's see. Yeah, so orders of business, again, The Mathematics of Space Exploration by Merle H. Arendt. And I got a new fan today, so it's a very nice fan. It's very British. It's not even branded. So we can do that as a some assembly required section, which I don't think is going to take very long. the Status 29-inch tower fan. Assembly of base 1. Position base to the main body and ensure the hole is in the right position. Position the base to the main body and ensure the hole in a right position and ensure the hole in a right position. Cool. So I don't think this is going to be a very challenging build. Even this chair was not too bad, but I'm also slightly amused because some assembly required is the name of my father's business. Oh. Right, okay. Those do not fit around each other. These go on each other. Two-handed. Okay, so that needs to go to the front. Hey, there we go. Yeah, like I said, not terribly challenging. Also very British. Hope everybody's been having a good week. Again, I just got back from my parents up in New Hampshire. In New Hampshire. We were somewhere around, was it 40 degrees north, so certainly the sun was rising and setting roughly the same amount, or roughly the same times. This point in the year, the sunrise and sunsets are not quite as pronounced as they have been in summer and winter. The differences are not as pronounced. All right, here we go. Oh, that's a timer. Gotcha. Oh, interesting. There's an on. Okay. We'll leave it there. I think that's going to be good. So we're getting a nice breeze from sort of behind us. Hopefully it'll come around here, sweep through the computers, bring some fresh air. Figure 2, secure the main body to the base and turn the adjusting plastic screw nut by clockwise. Printed in Romania. If any of these companies want a proofreader, I may not know Romanian, but like, righto. So that's one order of business down, score, and we'll get on to the second. Namely, looking at, oh, right, second order of business. Looking at the mathematics of space exploration. And again, we did do some of this earlier, but I kind of wanted to try and get some of the, like, more, like, how do you teach this stuff? Normally my, like, curricular days are Tuesdays. Oh, and I also sliced my finger up tonight. That was awesome. My son was having me help with his Pinewood Derby car. He's in Scouts. And we were kind of like drilling holes straight down through this thing, and I was like, we can kind of like angle a couple of them, and he's like, yeah, that's cool. So we got all that done. And then I was like, and we could do like a sort of cheeky one that goes like through the back like that. And he was like, yeah, let's do that. So I held it down like this, and I was cutting through, and it gave at the last second because all of the rest of the holes did. Should have realized. And the whole thing went slice right across my knuckle. So fortunately, it's not too bad. Unfortunately, it's very deep, and there's a lot of skin there. So it bled like hell, but then I was also an EMT for a few years, so, you know, put a lot of pressure on it. Wash it with soap and water before it closes up, and then put more pressure on it. Try to dry it best you can, and then we gauzed the hell out of it. So, hey Zach, how's it going? So yes, it was a comedy of errors tonight. Everything's fine. It's just slightly annoying. And yes, if anyone is at all compelled, we do have our charity stream that we're working with for the month of May. We're about halfway through the month, and I believe good things have happened over on D's side. 8-Bit D has been doing Game On to End Lupus, or GOtEL, for several of the last years, and nope. Alright, it looks about the same as when I left. View campaign. Yeah, anyway. If anyone is at all interested, the links are there. You can feel free to donate if you have the time, if you have spare cash. If you don't, no worries. And I, for some reason, can't get over to... There we go. $136,800, essentially. So congratulations to everybody on the GOtEL team. Goal is $205,000, and we're only halfway through the month. Not even quite. So that's really awesome. Congratulations to them. All right. So, yeah. Oop, nope. Not Merrill. Merle. Aren't. owe that person the benefit of spelling their name right. So, section 1.1 deals with linear motion. And when we're thinking about linear motion, generally speaking, we're talking about motion along, well, yes, a line, hence the name. Dope. Walk myself into that corner. But generally what we're seeing is a motion that is going to involve units. So for instance, our distance is going to be in something, usually feet, meters, miles, millimeters, right? Any other distance measurement that we could think of. And typically this is going to involve some sort of time, which is going to typically be given as seconds, minutes, or hours. And of course, there are many more units that you could use for time. Completely up to you what you need, what your use case is. Okay, now out of this stuff, we have distances, we have times. This is naturally going to allow us to come up with something like a rate, which you'll notice I have these nicely put almost in a fraction like that. Typically we're talking about unit distance divided by unit time. And typically this is going to be in feet per second, meters per second, miles per hour, and many other units, or unit combinations. So here we have a unit distance divided by a unit time. Again, dependent on use case. Typically you want to use something that's going to make sense for your particular scenario. You probably don't want to do feet per hour unless it's something that's really slow. You probably don't want to do miles per second if it is something that is really slow, like, you know, me walking. I will walk at approximately 3 miles an hour. Divide that by 3,600 and you can get miles per second. Not very interesting. Right, 1/1200th of a mile every second. Okay, so then we're going to talk about unit analysis. Now, typically what we're doing here is we're saying that we want to look at what the units are in a particular scenario and just ensure that they make sense for the larger scenario that we're talking about. The not just make sure that they make sense, but also make sure that they're in the right values, and it also can be used to verify what kinds of operations you need to do, what kinds of operations you need to perform. So for instance, if we have something in feet per second and we want to make that go into miles per hour, let's do that as 10 feet per second. Right? We want to convert that to miles per hour. Then typically what we're doing is we're going to say, let's take that 10 feet per second, and then we're going to multiply it by something. which is then going to move, change, convert one of our units from what we have, feet per second, into miles per hour. So if we want to change it into miles per hour, you notice that the hour is also in the denominator of the fraction. And therefore we need to convert from seconds to hours, put the seconds in the opposite location, and if you look at it, then when we multiply these things, our units can move just like our variables or just like our numbers do. When you multiply straight across. So if we were to multiply 1 second by, it's going to be 1 hour, then we end up with 1 second hour in the denominator. And then at the top, we're going to have 10 feet, right? That's just going to come along for the first part, where we're dealing with the time bit and trying to convert the time. My goodness. That's a weird rash. Okay. Sorry, just scratch myself or something. Anyway. We're going to multiply the 10 feet by how many seconds are in an hour. Well, I happen to know what it is. It's 3,600. If you don't know, you can always bump this out one further and say that we're going to convert hours to minutes and then minutes to seconds. That's a perfectly acceptable move. If we wanted to do that, we could do 10 feet to 1 second. Multiply this by, again, 60 minutes per 1 hour. And I guess I want that the other way around. Right, convert seconds to minutes. And then also convert minutes to hours. All right, 1 hour to 60 minutes. In this case, what happens, again, we're multiplying across the top. 10 times 60 is going to be 600, times 60 again is going to be 6 times 6,000, which is, or sorry. Oi. Yeah, right, if we multiply it all together. Sorry, 60 times 60 is going to get us 36 with 2 zeros at the end, so 3,600. Okay, and then that ends up being that number there. Also, the units are going to convert because here we have minutes divide out minutes, or if we multiply the units across just the same, then we have feet second minute divided by second minute hour. So our seconds and our minutes are going to divide out, which is going to leave feet per hour, which is one step closer to what we actually wanted. Okay. So here, again, 3,600 seconds per 1 hour. Again, those seconds are going to divide out. And then we're going to multiply again in order to convert our feet to miles. So we know that feet needs to go away, so that should be in the bottom. And miles should be up top because that's going to replace the feet. In 1 mile, there are 5,280 feet. And yes, we should definitely convert to the metric system whenever possible. So what we have here then is our 10 is going to be multiplied by 3,600 by 1. So we end up with 36,000. And that is miles as the only remaining unit up top, divided by 1 times 5280. Hours is the only remaining unit at the bottom. Okay. No matter how you did it, this is what we're going to get at the end. Then we're going to say, okay, let's take out any common factors we have. Nice, easy. We can get rid of a 10 from both of them, so one of the zeros get kicked out. And then we have 528 into 3600. So we can do the best we can, try to divide out individual numbers. Let's see, 512 is a power of 2. And since it's a power of 2, it should have a bunch of 8s in it. 3600 should also be divisible by 8. So if we we could also actually do this a bit nicer and say, okay, let's try to figure out what will divide nicely into these numbers. And then use our calculators, but you know what, it's fine. 3600 divided by 8, we're going to get a 400. 32 is our actual multiplier, right? If we multiply 4 by 8, we get 32, which leaves 4 as a remainder. 8 into 40 goes 5 times, and then we have a 0 left over. So 8 into 3600 is going to be 450 left over. Okay, and then 8 into 528. 8 into 52 goes 6 times, which is going to get us 48, which leaves us with a 4 remaining, and 8 into 48 goes 6 times exactly, so no remainder as well. So now we get 450 over 66. Are they both divisible by 6? Well, they're both even numbers, and the top number, 450, if we sum up the digits, we get 4 plus 5 plus 0 is 9. 9 is divisible by 3, therefore 450 is also divisible by 3. Since 450 is divisible by both 3 and 2, then it must be also divisible by 6. Okay, and then 66 at the bottom is divisible by 6. So that's nice. It's going to leave us with 11. And then 450 divided by 6 is going to be 45. 42 is a 7. That leaves 3 left over. And 6 into 30 goes 5 times, evenly. So 75 over 11 is going to be our final value for that. 10, right? 10 feet per second is going to be equivalent to 75 over 11 miles per hour. Not very fast, all things considered. So this is about roughly, right, 6.8 miles an hour. It's going to be just under 7 miles an hour. Right, if we want to, we can approximate that by getting the actual value. Okay, well, you know what, we can get the exact value because it's a very nice repeatable number. 6.81, repeat, miles per hour. 6.81 miles an hour is a healthy run for me. Could keep it up a while. It's actually an interesting question. I can do or at least I could when I used to do them. I could do 5 kilometers in 45 minutes. I'll grant you this was This was a number of years ago. But roughly speaking, right? I know that in order to get from kilometers to miles is approximately, right? So this is approximate. There are going to be 8 kilometers in 5 miles. And there are 60 minutes in 1 hour. So we could figure out what 5 kilometers in 45 minutes is going to be in miles per hour by setting it up like this. So again, kilometers are going to divide out, minutes are going to divide out, and then we're left with miles per hour. Up top, we have 5 by 5 by 60, or we could take out individual values now. So that might actually be more preferable. We have a 5, which can be taken out from 5 and 45. 45 divided by 5 is 9. 8 into 60, they both have a common factor of 4. So 4 from a factor of 4 taken out of 60 is going to leave 15. A factor of 4 taken out of 8 is going to leave a 2. Okay, and then we have a factor of 9, or we could take a factor of 3 from 9, which leaves 3 behind, and a factor of 3 from 15, which leaves 5 behind. So overall, up top, we've got 5 miles times 5. So that's 25 miles. Not per hour. I cannot run that fast. And the bottom is 3 by 2 by 1 hour is going to be 6 hours. So I could, in theory, although I definitely cannot keep it up that long, run 25 miles in 6 hours. Right. But that is just an average speed over that 45 minutes that we were talking about. So what is 25 sixths? Just over 4 miles an hour. All right, 4 and a sixth, 1 extra sixth miles per hour. 1/6 is 1.6 repeated, I think. Right, leaves a 6 behind, bumps up a 3. Which leaves 9. Yeah, pretty much. That carries 1 all the way through, so it leaves 25 at the end, if we kind of cheat a little bit with, because of the infinite nature of this thing. Righto. So approximately 4.16 repeated miles per hour is going to be my average speed for a 5K. I think maybe these days a little ambitious, but I'm more into riding bikes anyway than running. It's terrible on the knees, especially if you do it improperly. Okay, so this is how unit analysis works. Thank you for the follow. With my rambling nonsense. Okay, so that's unit analysis. Now, in the middle of all of that, you also heard me say the word math man, math man, math man. Absolutely. Once I actually get DaVinci Resolve working, then I plan on making a bunch of our alerts are going to be not just Math Man, but like all Square One TV related. Okay, so we're going to talk about average speed. And average speed is going to be the speed, which is an average. We can calculate our average speed. Also, typically referred to as the average velocity, typically referred to as v sub a or v bar. A lot of times when you put a bar above a variable, that means that we're going to have an average of that thing. All right, so average speed over any particular time period or anything like that. I know, right? Now, I guess Cyber Chase was actually pretty good too, and they did get Gilbert Gottfried and Christopher Lloyd in there, so like that's pretty cool. But I didn't really watch it when it was actually out, and then my kids started watching it like a few years ago, and I was like, it's all right. Yeah, not biased at all. I actually went to a in our mall. They had a Where in the World is Carmen Sandiego tryout, and I filled out the form, but they never contacted me. So I know, right? Yes, I definitely wanted to be on that show too. I'm thinking to myself, would I, knowing what I knew, and I was the Geography B champion for our school for 2 years of the 3 that I was eligible. And I went to regionals once. So I went to our state B. Right, but that was during the same time period too. I'm pretty sure I put that on my application that I was like, school champion or something like that. But I did also go to a school with 30 kids in a class maximum. In a year, I mean, like 30 kids in a year. Most of our classes had 24. We had 28 one year, and we had 30 for about 2 days once. But then somebody ended up moving classes, or moving schools. Right, so our average speed is going to be calculated. We're going to look at the V final minus our V initial. And I'll tell you one thing. The book lists these. Oops. I don't know how you feel about that, Zach. It's always listed as VT, and it's terminal velocity. I actually wrote in my I actually pulled out a pencil on the plane and started writing in my book. And it says, "Oh, I don't like that." Yeah, I was sitting next to a kid who was I was sitting next to a guy who was probably in college, maybe just out, and yeah, I'm pretty sure I got a side eye like, why are you writing in a book? You got a physics problem where phi and theta had opposite meaning in spherical. Oh. Right? So then you're like, intuition is just thrown completely off. Now, I don't mind what the intent was. I do mind the fact that they used terminal velocity, in that it's always considered like the maximum speed that you can go through a particular medium. But realistically, right, if you were to break it out and say, what does it really mean to have a terminal velocity? This means really the speed at which acceleration is 0. So, like, yeah, if we're talking about a time period over which our speed has been increasing or decreasing, then yeah, probably at the end of that time period, the acceleration has stopped. And so the acceleration would be 0. And so it technically would be our terminal velocity, because that's where it ends. But at the same time, like, we could just be looking at a certain window of time where the trend still continues, the acceleration still continues. So it doesn't have to be where the acceleration is 0. They're just using it as the end speed. And remember that end means terminal. So, you know, we could throw around these terms a little bit and make them a bit more interchangeable. But at the same time, like, come on, man. Ooh. Oh, why didn't that work? What? Hey, boys and mouse. How's it going? Been seeing around the elements lately. Welcome on into this one. Let's go for it. Sure, I can try. Can't guarantee that I know it. Okay, so our average speed here, while you're typing that up, your average speed here is going to have the same units as other speeds that we were looking at earlier. So we want this to be, you know, miles an hour, or feet per second, or meters per second, or feet per minute, or whatever it's going to be. So in this particular case, again, here we've got our distance. That is not it. Hang on. That is not a distance. No, I messed that up because average speed is actually just going to be the sum of these two numbers, our final velocity and our initial velocity, and we're going to divide by 2. Okay? What I was thinking was that there is another way to do this, and for this one we talk about our distance at the final moment, and we subtract that from our distance at the initial moment. And here, this is where we get our distance. We want to know how far we've gone. What's the difference, or what's the distance between these two values? Okay, and then the denominator ends up being our time. And again, how far are we going in time? So t final minus t initial. Okay, whereas this one here is just a numerical average. Right, and like I said, we're using velocity and speed as interchangeable terms. Technically they're not, because you need to think about like what direction the velocity is going in, whereas the speed is just the numerical value. I don't know if I should say numerical average. Arithmetic average is the proper term for it. Right? Arithmetic average is when you sum up all the things and divide by how many things there are. Again, our average speed is just the sum of our initial and final speeds and divide by 2, which should be equivalent to taking the starting and ending locations, figuring out how far it went, and then taking the initial and final times and figuring out how long that is, dividing that by that. So you should get the same thing in both places. If you don't, you can blame Zach or something. I don't know. Seven hours back, 5:30. You might be having dinner. Okay, and then we could also do average acceleration. Now we could do the same thing here. A is typically acceleration, and then we could put our A, capital A, down at the subscript, or we could make that a bar to show that it's an average. And again, here what we're doing is we're just going to say, okay, well, we'll take the final acceleration and the initial acceleration and add them up, divide by 2. Or, again, we could go with taking the velocities, the final velocity subtracted from the initial velocity, and dividing by our time, final minus initial. Again, same as what we did up there. With our average speed taking the distance. So we're going to take our right, instead of velocities, we're going to use accelerations. And then the same thing again happens with our average acceleration and average speed. We're looking at the kind of component terms that make up our speed. So speed, again, feet per second. We have a distance divided by a time. And in this particular case, it's going to be, again, distance over time. Acceleration, we can also look at this in terms of unit analysis. What do we have here? Well, our velocity is in feet per second, and then our time in the denominator is in seconds. So now, like, what do we do with that? Right, probably the easiest thing to do is to multiply both top and bottom by seconds. Up top, we get rid of the fraction because this is feet per second times seconds. So those go away. Then in the denominator, we get seconds squared. Right, this is feet per second squared. Or we could say it as feet per second, which is the same as what we have really here. It's the easiest to see it. So feet per second, is saying that our velocity is increasing every second or decreasing every second based on the acceleration value. Again, that simplifies to feet per second squared. Okay. Now, Poison Mouse, if you have posted it somewhere on Discord, let me know. 5-minute ad break warning, just to let everybody know. We'll be starting, and then take a little stretch break, get up, cycle water, see how things are going. New coffee. It's pretty good. Now I gotta figure out where I got it. Okay, so our accelerations are going to be in distance per time squared. Our velocities are going to be distance per time, and our distances are just going to be distances. Okay, now how do we come up with an equation which then starts talking about our distance and our rate and our time in a more comprehensive manner? So something that starts getting more terms involved in it, not just distance, rate, and time, but like, what about the one that involves acceleration? Right, so distance is equal to a rate times a time. Realistically, we can also call R our V for velocity. Right, so D equals R times T. You know what, let's move that down a bit. There we go. Distance equals rate times time, or distance equals velocity times time. Well, what about our velocity? Okay, if an object starts with 0 speed and then reaches its final velocity, then it's average. See, I'm using the speed and velocity interchangeably, but I shouldn't do that in the same sentence. Alright, starts with 0 velocity and reaches final velocity, then its average velocity will be represented by right. Alright, V bar or V average is equal to VF plus VI over 2, which was just final velocity plus 0 over 2. So a distance is going to be equal to its average velocity times time, or it's going to be equal to v sub f plus 0 over 2 times t. Oops. That'll work. So d is equal to 1/2 times v final times t. Okay, we'll be right back. Ad break. There we go. There we go. Aw, all blurry. Is that gonna catch me from here? Probably not. Oh well. I was wrong. So, anybody who doesn't know, I also study eskrima, which is a Filipino martial art that has to do with using machetes. This is not a machete, obviously, because otherwise I'd have a lot more cuts on me. Just the one today. So in eskrima, we are attempting to defend ourselves against any number of threats, but typically the way it was developed was that there were a group of like crime families that were trying to steal workers' wages, and these workers often worked in fields, and in fields or jungles you had machetes. So let's see. Come on. Boo. Alright. Well, try to do the best we can. And typically what would happen is that the workers would resist, and then they'd have to fight their way out of various situations. And once it, word got around that the workers were fighting back, the crime families typically moved on to other people. There were like neighborhood watches and things like that, all with people who learned how to do eskrima. So it was banned by the Spanish when they came and colonized the Philippines, because they were all worried that like the Filipinos would be armed, with machetes, which they were. So they could no longer practice eskrima with large weapons, and so they had to start practicing with sticks. And so often they're called kali, or eskrima sticks, or various other things. Anyway, the setup we were doing here was our what's called sticks to heaven. So we come off, have one over the shoulder and one at our hip. Typically we are attempting to point both of the butts of the machetes at our target. So right now you can see not much in profile of these sticks from where you are. So then we're looking to strike at 45-degree angles, come back up, 45-degree angle upward, and then swap. That's actually kind of a big deal. So this comes up, and then the wrist turns over as both things swap, and then it returns to now the left side. Now when we're on the left, we do the same thing. So 45-degree angle, return, 45-degree angle up, twist, swap, and back to right. There's a lot of stuff that we learned how to do from here, and we only did like a few things just like a few weeks ago, and now I'm losing it. I'm completely forgetting everything. It's terrible. But let's see, we were doing one where we come up over the top and into a fan block. Actually, it's out only half of the fan block. And then from here, the one at the waist comes across. The one at the top then goes into it looks like a comma when we strike like that. Yeah, I forget what he called it. Anyway, my instructor's going to be so disappointed. This one's coming up, this one's coming over, and then this one's coming back down. So we do this a bunch. We also did, let's see, we can come from the shoulders and do strikes on this. So we can go strikes down like this, strikes up like that, and then we go to the other way. We can also do that from here, where these strikes go down, these strikes come up, return to the shoulder, and then from here these strikes come up, and then these strikes come down, return to the side. So we could do a number of different things. And there's also can do a number of things from right. When we do one-handed stuff, usually we want to practice both sides as well. And we can do stuff from closed guard like this, where we strike out. These are just basic hits. And then we can do, let's see, number 2 is just striking twice. Number 3 is striking over the top and hitting. Let's see, number 4. No, I don't remember which one it is, but one of them is a fan block. think that's like number 4 or 5. The fan block comes up and does a backhand first to block, and then a forehand to strike somebody's stick like out of the way, or you're tapping it so that they'll grab it a little bit harder, which is actually what you want, because what you do is then you come around and hit their hand, which again, if you remember, this is machete. You're going to take their hand off. At the very least, off the stick, off the machete. So this gets to be like extremely dangerous stuff when you start talking about the actual real applications of it. But generally speaking, you're talking about people who are trying to kill you, and so you don't want that to happen. So what's a hand between friends, or rather, not friends? All right, so back, forward, strike, regular. I think that's a kadlik, is what that one's called. So we're coming from here, and then like whipping around, and then giving a single strike. One of the things that we had done was that we were trying to do like, you're going to do a single one, and you strike and come across, and then from the outside we do a single one and then come across, and from here you do a 2, come across, from here you do a 2 and then come across, from here you do 3, which is single over the top, single, and then come across. From here we do a single strike over the top and a single, come across, and then we do number 4, and then we come across, and then from here we do a number 4 as well. I think this one's different. It's not just the fan block, because now we're in the wrong position. Yeah, I don't remember what this one is. Number 4 from this side is similar, but it's not the same. I think it might just be here, over the top. No, it's not that way. Here. Nope, not that one. I'll get it right one of these times. It might be that, where we stop here and then immediately use that momentum to go into an overhead strike. This would come down on top of somebody's head and then come back and pop again. Anyway, I will learn some more stuff in Eskrima and show off some other time when somebody wants to redeem these. Good form. If anyone also wants to redeem good form, I will often ask what kind... I will often ask what kind of martial art form you'd like to see. I know I've done 17 years in Tang Sudo Karate, so I am a first degree brown belt, which seems like I should be a black belt if I've been in there for 17 years, but 3 were COVID, and 3 I was working on my master's, so like it was kind of non-existent or touch and go for a little bit of that, and then that's down to 11 years of active work, and then I'm also just kind of slow at remembering stuff, so okay, so then yeah, right. I've taken Eskrima for the last year and a little bit, and then also for the last 4 to 6 months, I've been going over to my instructor's house, same guy as does Eskrima, and learn some Tai Chi. So that's been fun. That one's a little more touch and go. I mean, he's just not at the home as often for that. Sometimes he's just literally got to do work or on a vacation that takes up a Friday. So I don't fault him for that. Okay. So if we have an average velocity, that takes us here, which then our distance is now going to be in terms of our final velocity if we initially started from 0 velocity. Then, interestingly, right, acceleration also had this sort of stuff. So if we started at 0 velocity at 0 time, then also our acceleration average should be equal to v sub f minus 0 for our initial velocity, and t sub f minus 0 for our initial time. We can mark 0 time whenever we want, so I choose to make it at the initial moment, at the 0 moment, or 0 velocity moment. Which means that a bar is equal to vf divided by t sub f, which also means that this is going to be, nope, don't do that. Which also means that v sub f could be equal to a bar times t sub f, which can go into here. And now d is going to be equal to 1/2 times, parentheses, a bar t sub f times t. Now, technically, these don't necessarily have to be the same as each other. However, we are going to say that whatever time we pick is going to be the final moment. So t sub f and t are really just the same thing. So our distance is going to be equal to 1/2 times the acceleration, average acceleration, times t squared. All right, and typically, doesn't always have to be the case, but our acceleration is constant. Now, it doesn't have to be constant, but most of the time that we're doing stuff, it will be. Or at least over certain time periods, it will be constant. And then once we get outside of that time period, it will change to another constant, for example. And so that's going to end up making this just a slightly simpler version. D is equal to 1/2 at squared when moving from rest. So here, v0 equals 0 at t0 equals 0. Right, and our average velocity is just going to be a constant velocity over that time period. Again, vf, so our final time divided by our final velocity divided by our final time. Those are just simple constant values. So they're not going to change at all. So, right, the acceleration over that time period. It's just going to be a constant divided by another constant. Okay, so what happens if it's not going to be from rest then? So what happens if we start from moving. What happens if we start from an initial speed of not 0? Well, let's see. So we should be able to do the same thing that we did here. If we do a non-zero initial velocity, then d is going to be equal to v bar was v final plus v initial over 2 times t. du is equal to 1/2 v final was again acceleration times time times time plus now 1/2 v initial times time as a separate term. Now I have a problem with that. Namely, that when we usually do stuff, we use a formula that is just v0 times t. It does not have a 1/2 attached to the front of it. So that makes an interesting problem. Because that should not be there. So there's probably a 2 that should come out of somewhere. But now I'm having trouble seeing where that would come from. So I have apparently painted myself into another corner. In order to be logically consistent with the algebra, right, this makes complete sense. However, it's not actually how things work. Wait. Ah, but A bar A bar is not v sub f over t sub f. A bar should start right, our acceleration, provided that it is constant, a bar should be equal to Vf minus Vi, V initial, divided by T sub f minus T sub I. Okay, in initial velocity, t sub I is going to be equal to 0 still. Okay, but v sub I is not 0. So initial velocity, right, this is going to be, I might be painting myself into a different corner, but nonetheless. I think we're okay. Okay, a bar times t sub f minus t sub I, which again is going to be 0. Right, t sub I is equal to 0, is equal to v sub f minus v sub I. So therefore, v sub f is equal to v sub I plus a times a bar times t sub f. Okay. Which means, right, we'll not do any of this just yet. Okay, we come through here, and we say that from up here, d is equal to 1/2 v sub f times t, where v sub f is replaced by this term. So now d is equal to 1/2 v sub f is v sub I plus a bar t sub f, which again we're just going to let be t times t. That's better. Okay, we got it now. No, we don't. Hang on. Ah, damn it. We still got that 1/2 stuck in there. Wait. Because it's not... v bar. Because it's not vf, it's v bar. Maybe. No, it's just v bar times t. Okay. Man. Okay, v bar times t, which is vf plus vi over 2. Yeah, okay. Damn. But vf has a vi in it. Okay. There we go. Okay. This is better. So vf is replaced by v sub... Yeah, let's go the other way. A bar times t sub f, which is just t, plus a... Nope. Plus v sub I. Plus v sub I all over 2 times t. All times t. Okay. There we go. That's better. Alright, now we can see. Famished! Thank you so much for the bits. And thank you for hanging on in there, hanging out with us, having a good mathy time. Yeah, there you go. I mean, it was spelled right up above. It just didn't have an at, so. All right. Okay. So, did I mess that up again? Quite possibly. Oh, no. I can't, right. I can't change it out because now it's that value. Right. Okay. We're good. So this is going to be a 1/2 a bar, which is just whatever acceleration we're doing. It's a constant times t squared. So that t there bumps in, gets distributed to all these terms. Plus, this is 2 v sub I over 2 times t. There we go. All right, look at that. Do I have a cold? No, I just cough all the time. I mean, it's quite possible that I did pick up something on a plane or who knows what. This is our v initial times our time. Times 2 divided by 2 is just 1, so those are gone. There we go. All right, this is way better. Yeah, no, it's the shape of my nasal canal. Just keeps sending stuff on back, and I keep coughing. So it's very unfortunate. It's been happening to me for 30 years now, so yay. My dad, my scoutmaster, everybody was like, man, just, you gotta stop doing that. I'm like, I wish I could. Please. Okay, so when we have a non-zero initial velocity, this is what we get here. Where this is going to be our, what's also called displacement. Or in other words, how far did we go from the initial point all the way out to wherever we end? Right, and so they were like, oh, just, it's a nervous habit, just don't do that. I'm like, no, I keep coughing stuff up, so clearly it's not that. Okay, so typically displacement is listed as S of t is equal to 1/2 a t squared plus v initial times t. And then we also oftentimes get a final term on this, which is plus di, or d sub 0. It's the initial location, so like wherever we started. Displacement oftentimes is listed as not just d for distance, like distance from where? Well, it's from like a place. What place? Well, whatever place we mark. So d initial is going to be that place that we marked as like our 0 point for any particular location. So oftentimes they'll be like, okay, well, it's d minus di, which is the displacement overall. How far did you move? What's the distance total between where you started, where you ended? So d final minus d initial is going to be our displacement, which oftentimes we'll just call it s, or we call or we move that over, and then the final distance is going to be our d sub f, which is going to be equivalent to s of t. So it kind of depends on what you want. Oftentimes in the book, I believe that they refer to s of t as just like that non-zero velocity function. So the stuff without d sub I. Hey Zyphon, how's it going? Good to see you. Welcome back. That's right, you were doing topology earlier. If anyone does not know, we've got so many people to shout out. If anybody does not know, Zyphon SVC, they do math, so go check them out. There are also our list of the math chads. Who are listed here. These are all other awesome people that we have on our list, and we have like probably 4 more lists worth of people that we could throw out there. So if you would, if anyone out there wants to join the Elements crew, feel free to head on over to Penn Center's Discord. That's kind of like the central repository Discord for all of our mathy type friends, and yeah, talk with Penn Center and a number of other of us. Join the community, and you know, you can get your name on one of our other $ commands there. Anyway, yeah, what you been up to apart from topology? We've been working on The Mathematics of Space Exploration by Merle H. Arendt. This was actually a textbook for the Maple Grove High School back in like 1969, I think. This was printed in 1965 and has been sitting in the attic of one of my friend's fathers, who was a math professor, probably since about the 1970s. Undergraduate compendium, nice.
Find top-rated wellness products on Amazon, like these aromatherapy candles with 5-star reviews. I saw fantastic value.
Yeah, I got back on Tuesday morning, or Tuesday afternoon. When was that? That was yesterday. From a trip to go see my family in the States. So we are currently living in the UK. Anybody who doesn't know, hasn't been following the channel. My family's been here for about a year, and has been, we've been doing great stuff and hanging out and going and seeing all sorts of places all over Europe. Usually go back to the States for, well, the plan is to go back to the States for like a week here and there. But so far the kids haven't been back, and we're planning a trip for August to go see some other family members. One of our other family members is getting married, so much happier than what I went for just now. So my grandfather passed in October, I want to say. I did a stream dedication back then. So anybody who wants to see that, it's in my Satisfactory stuff. Most likely, I think that is now on our YouTube. At Obi-Wan Pez is our gaming channel, and at NSimplexPachinko6542 is our math content channel. So feel free to go check those out. The dedication of my grandfather is on the Obi-Wan Pez channel for Satisfactory. So go check that out. And his sister, well, one of his sisters passed like super suddenly. I want to say just before that. It was some like aggressive brain tumor. And then his other sister, the baby of the family, passed in November, December. I have a thing. I should look it up. It was December. And so yeah, it was kind of like all three of them very suddenly, or well, not that suddenly, but just kind of all three of them almost at the same time. So we had a memorial service for my great aunt, and Grandpa did not want a memorial service, didn't want people crying over him. So instead we had a joint ceremony reception afterward for all of us to get together, have some snacks, share some stories of the ridiculous stuff that they did. Yeah, one of the stories that we always heard about was my grandmother was, gosh, like second grade or something like that, so like 8, 9, third grade, somewhere in that area, and had her pretty new white dress on and made friends with, I think she was the new girl in town, so she made friends with this lady who was my eldest great aunt, and they went home. She asked if she could come over and just hang out for a little bit after school, and so she came over to kind of get the lay of the town, get to know some new friends, and my grandfather was tending to the farm. He had chickens. Absolutely hated cats for that reason, because the cats would always get in and kill the chickens. And he was tending to the chickens and harvesting by chopping their heads off, and then taking those in for food. Well, he would have a habit of chopping their heads off and then putting them on their feet. So they would run around like chickens with their heads chopped off. It was quite literal, and it was spraying blood everywhere and got all over my grandmother's brand new white dress. And he stuck his hand out and was like, "Hi, I'm Herb." And she's like, that was how my grandparents met. He had to be about oh, that's interesting. What age were they? Because he would have been a couple of years older. Oh, is she younger than he? Okay, yeah. Okay. Yeah, I couldn't remember the birth order, but my eldest great aunt was younger than my grandfather. That's how that worked. I thought she was older for a minute there. She just acted like it. Alright, anyway. So we get this displacement formula, which now works out very nicely to get us the 1/2 AT squared plus V initial t plus D initial, which gets us the whole formula for whatever distance we want at whatever time we want. So, automobile slows down from 50 miles per hour to 20 miles per hour in 10 seconds. So, what is the rate of deceleration in miles per hour? Oh, oops. Right, deceleration cannot be just miles per hour. This is an acceleration. This is going to be miles per hour per second. How about in feet per second per second? So this does become fairly easy to work with. Most of the time we're going to say, okay, well, we have a formula for this, or we can work through it, reason through it, right? Our unit analysis is going to tell us that this is going to be a rate of deceleration. So we know it is going to be an acceleration of a kind. We said that we wanted our V final minus our V initial divided by T final minus T initial to get our average deceleration, but in this case it's going to be a linear value anyway, or sorry, it's going to be a constant value anyway. The acceleration was constant throughout the whole time period. So this is equal to our final velocity was 20 miles per hour. Okay, minus our initial was 50 miles per hour, divided by our final time was 10 seconds, minus 0 seconds was our initial time. So when did we start our little stopwatch system, right? It's at 0 time. So that is going to get us a negative 30 miles per hour divided by 10 seconds. So this is going to be a negative 3 miles per hour per second. All right, since it's minus 3, negative 3 miles per hour per second, we could also say the, right, A bar is this, rate of deceleration is 3 miles per hour per second. Okay, so the implication is in the wording itself. Rate of deceleration implies that we are slowing down at a rate of 3 miles an hour per second. So it is a negative acceleration, sure, or it is a rate of deceleration. Okay, what about in feet per second per second? So here we've got 3 miles per hour per second, and we want to translate this to feet per second per second. So here we want to trade miles per hour for feet per second. So now we have to do that. It was the same thing we did earlier, I think, just in reverse. We did feet per second to miles per hour. So here we want to multiply, right, technically if you want to drop this over a 1 and say that we're going to do all the trading up in the top, that's fine, it doesn't matter. Right, we're going to get rid of miles and put in feet. Right, what are the values for that? It's 1 mile for every 5,280 feet. Okay, and Hours, we want to get rid of that and put in seconds in place of it. 1 hour for every 3,600 seconds. We did that earlier too. Alright, so now our hours are going to divide out, our miles are going to divide out, and now we just get feet per second up top and a seconds down bottom that always just stays there. So, do I need to do that? Yeah, that's fine. The other option is we could have gone through and said, what's the common factors, or what is the greatest common factor between 5280 and 3600? We could have figured that out earlier, and then it would have made this a little bit easier to work with. Let's see. So let's do divisibility rules, right? 5280 is divisible by 10, which is a 2 and a 5. And then 528 was divisible by 8. Yes. And that left behind, when we did divisible by 8, that left behind 66. So it was 8 and 66. I'm just going to do this over on the side here. So 5280 is 8 and 66. 660. $3,600 is obviously 136. This is 2 6s. This is a 5 and a 2. I mean, it's 10s, but we got it to match up. Let's just don't mess up a good thing. Right, so where are common factors? We've got a 10 and a 10. We've got 6 and 11. So we've got a 6 here and a 6 here. We've got 2 and 4. And here we've got a 2 and a 5. And a 2 and a 3. That still remain. Right, so now we can get rid of a 4 on that side and the 2 and the 2 on that side. Which leaves us with a 5 and a 3 from the 3600, which is 15. Okay, and then 5280, we have a 2 and an 11, which is 22. So anytime that we now see 5280 over 3600, we can replace it with 22/15 and be confident that we're just going to always get that particular setup. So this is going to get us a, 3 by 22. I know it's coming, so I might as well. Divided by 15 is 3 by 5. This is feet per second per second. 3's divide out. We now get 22/5 feet per second squared. Or, this is an exact value, 5 goes into 22 4 times evenly. And then point, and now we have 2/5. 2/5 is the same as 4/10, which is another 0.4 feet per second squared. Right, that is also equal to our acceleration A. Or A bar if you want, but it doesn't really matter. Again, we talked about this. The average acceleration is just the same as the acceleration this whole time through. I guess if you want to get technical, right? Because you're not always going to be pressing the brake pedal at the exact same rate in the exact same way every single time. You're not going to be burning off the exact same amount of energy in your car every single second. And like even smaller than that, right? Every single millisecond, you're not burning off exactly the same amount of energy in your car, kinetic energy. So it's not going to quite work that way. But we can say, again, on average, that's why we really have average acceleration. It's going to be as close as possible to that value all the way through. We can kind of pretend. It's fine. If anybody wants me to do any other mathy type stuff, let me know. I did have a couple of people who said they wanted to give me problems, but I haven't seen them. It could also be that you put it in Discord, and if you did, I haven't looked yet, so sorry about that. Discord was giving me some problems earlier, so I closed it. It's fine. Ooh. Somebody named Mataratos posted ODE systems, so I'm tempted to go and do those. But anyway, 1-2. So, question. An automobile traveling 45 miles an hour. It comes to a complete stop. In 10 seconds. After the brakes are applied, naturally. Find the deceleration in feet per second. Find the distance required to stop. Right, so that becomes interesting because we didn't really talk about, like, what's the distance required to do any of this stuff. We did talk a little bit about, like, the distance formulas that we had up there based on acceleration. So we can do that, but we didn't explicitly talk about it before. Okay, so our rate of acceleration, deceleration, is going to be equal to, same deal again. This is going from v final minus v initial over t final minus t initial. Again, this is just going to be v final is 0 minus v initial is 45 miles an hour divided by t final was 10 seconds minus 0 seconds to start. Now this is also telling us immediately that we're going to go from miles per hour per second, which is what we have naturally, to feet per second. So we're going to have to set up that conversion, but it didn't have us do the middle step where it said find the deceleration in miles per hour per second. So that makes it interesting because this just like jumps into it and says, haha, here's what this is going to be. Oh, did somebody actually already answer this? No. Okay. Okay, so this is going to be a negative 4.5 miles per hour per second. Again, we're going to have to do the same conversion that we did up above, but guess what? We already did it. So we can now just use the final conversion rate, which we know is going to be 22 over 15, right? 5280 feet per mile and 1 hour per 3600 seconds. So this 22 over 15 is going to directly just jump into miles per hour, converting directly to feet per second. Now we could actually put those in and make it feet per mile times hour per second. It's all right. Right, the unit, again, is actually foot hour per mile second. So what does that mean? It's just a conversion ratio at that point. So it's not going to be massively useful for us to like really get into it. Okay, so our acceleration is going to be negative, and also we could convert this to negative 9 over 2 if we really feel like it. It works to try to get rid of some of the factors. So 9 over 2 times 22 over 15. Again, here, this is going to be feet per second per second. We have a common factor of 3 in both the 9 and the 15, which comes out to be 3 over 5. We have a common factor of 2 in the 2 and 22, which comes out to 11 over 1. Which is going to make this a negative 33 fifths feet per second per second. That number, for some reason, does not sound familiar. I might have left it in an unsimplified form. Nope, okay. That's what I got. Okay, this is also equal to negative 5 goes into 33 6 times. And since it's fifths, this is going to be a terminating fraction. Makes it very nice. Times, here we have 3 left over, so 3 fifths is going to be 30 tenths, or no, sorry, 6 tenths. Wow. 30 50ths technically, but that's terrible. I don't want to do that. Anyway, 6.6 feet per second per second. Or if we want negative 6.6 feet per second squared. Right, same thing, all good. We might have just gone to ads. Boo. Yes, we did. And it didn't pop up. Okay. So it's going to be 3 minutes. If anyone does not have ads running, do you have any questions? Clearly, we need to do another thing. Also do a little bit of Tai Chi just because I feel like it. And it was good in getting our all the synovial fluid, is that right? I think that's it. Moving into all of our joints. So works out very nicely. Hopefully that won't cause my finger to bleed, but anyway. We got moving kind of nice. Try to let your just arms swing and then use a little bounce in your legs to cause them to actually move. So if I don't do that, they should just end up resting at my sides. But if I give it a bounce, it should start acting like when you push a kid on a swing or something like that. Until you get to a height where the same amount of bounce is going to put the same amount of energy into the system. Same amount of energy into the system as you're losing. And you can cross them over and let one go higher than the other, that sort of thing. Try not to let them go higher. You can make them go front to back. And then when we get nice and loose, our motions have been kind of 45-degree angle in your back foot and straight forward in your front foot, and our the amount of weight on each foot is about the same, and you want to make sure it's fluid so you can move back and forth easily. And our ward off is gently bringing the front hand up. It's going to be kind of curled out to the side here, and then lightly keep the elbow kind of in this place here, and then the back hand comes up and points toward right, and get your butt tucked underneath your tailbone, tucked underneath your spine. Keeping this frame is super important, and if anybody has done ballroom dancing before, it's the same sort of thing. It's just now you're doing martial arts with it. If you let this go and you like push against each other, you and your partner push arms against each other, it becomes tiring super quickly. And then if you like put the frame in place properly, you can actually hold this for much longer. It's kind of amazing. So what we had done was end up moving in kind of an interesting way here. So we start from our form, started from neutral position, bring our arms up, and then sink back, and then push down. We make a little ball, go almost entirely onto our right side, and then step left, and we're carrying this ball here, and then we step to the front and go into a ward-off position, and then we sink back just a little bit, bring the left arm back and keep the right arm where it is, so it's kind of like it's staying in space, which is a little weird, but it works. And then we bring this to the right just a little bit, which opens up a certain set of muscles, and then we move this. Nope. And we move this. Oh, what the hell? We move this back to the left. How do we get there? Move it to the right. And then we come around here. Right. Push. So we brace. And then shove out. And then push gently. Sink back. Come back forward. And from there, typically we go back into a ward off. And we can do this as many times as we want. If you're really good like my instructor, you can do it on both sides, but I am I am not at all good at this, so it's very, very beginner. Although he did say that I learned in about 2 weeks what it usually takes him 6+ weeks to learn, to teach everybody else. Mostly because they're like older people who are not there for martial arts and have not done martial arts. They are there for, exercise, keeping everything kind of loose, which is really awesome. All right, so we are going to go into the repository of Maine Lingo, a wicked good guide to Yankee vernacular by John Gold, and we're going to find a random page here. It is S. We'll do 2. Okay. So first, we're going to do Set Fire You, which is an admonitory exhortation of obscure origin. Now, set fire you. Pay attention to what you're doing. Set fire you. And, not what you think, but shag. Not a Maine exclusive, but because of the ubiquitous cormorant, or shag, that infests the Maine coast, it is a very common word in numerous allusions. It is inedible because of its exclusive diet of fish. Its worst offense is to clean out an entire pocket of herring awaiting transport. Shag. So, a shag is a cormorant, which is a fishing bird. So it goes after especially herring that have already been caught in a net, or are in like a bin somewhere. Like it'll go after all of the herring. And cormorant is inedible. Again, due to its exclusive diet of fish. So that's where the word shag comes from in a Maine orientation. All right, popped into chat just there. Again, is our YouTube channels. So come see at Obi-Wan Pez and at nsimplexpachinko6542, depending on what sort of content you want to see. Currently, we have 11 followers for Obi-Wan Pez. And last I checked, over 120 for nsimplexpachinko. Or, okay, maybe that's a lie. Hang on. Yep, we're at 130. So thank you to the half of you who joined in the last 1 month. That is nuts. 65 new channel subscribers in the last 28 days. Due to the fact, I will admit, right? Due to the fact that Twitch decided that all of our stored up videos need to go. Granted, right, we only had like 2 views on each of them, and it's taking up a lot of space on their server. So we did finally, I've been meaning to do it for a long time, finally move stuff to YouTube, and now subscribers are coming in. So awesome. Thank you so much, everybody. And if you're on YouTube watching this VOD now, yes, you. Awesome job. Thank you. Okay. So here we had our deceleration of 6.6 feet per second squared, or acceleration of a negative 6.6 feet per second squared, or feet per second per second. And now if we want the distance required to stop, we're going to use our D formula from earlier. We said our the deceleration formula was going to be 1/2 AT squared yeah. Just have to argue with myself. So the way it's working, right? So the way that I'm seeing this in my head is we're actually starting with an initial velocity of 45 miles an hour and decelerating which should, in theory, look something like this. Right, we're starting at a certain speed, 45 miles an hour. This is our distance. We're going from however far away we are all the way down to where we end up stopping. Right, we'll call that 0. But what d equals at 1/2 at squared is doing is we're starting at 0 and then like accelerating for 10 seconds. This is going to take 10 seconds to get from, right, our distance, which we don't know what it is. So this is like our final distance. I mean, it's kind of like our initial distance. So how far away from the end point do we start? We have no idea where that end point is. We'll just call the end point gets called 0. Right, we have no idea where that is. But that's okay. And on this one, we say we're going to start... Well, no, because this is backwards too. Right? So this is starting at 0 and then accelerating until we reach t equals 10. Right, d equals unknown. You know what? It's not doing that either. Ah. This other one is incorrect. Hang on. This is not what it looks like. because our acceleration is a deceleration. So we're saying that the way that I'm thinking about this is that this is a slowdown from an unknown location. No, come on. Okay. Oh. Here we go. Okay. Okay. So our initial loss of speed. Hang on. The loss of speed is going to be okay. The loss of speed is going to be linear. Okay. Our speed is going to reach 0 when our distance is going to stop changing. Okay, we're going at like the same speed until we hit the brake. And then this stuff right here. Yes. Okay, we're good. Yeah, that's how this works. I guess it's pretty much the same, but the way that it's working is that we're going to, at a certain location, we call it 0, 0, we're going to slam on the brakes. And the initial distance that we're traveling is going to be a lot, right? This is going to be a steep line because we're going to be traveling a lot of distance in a short period of time. And then as we get slower or as we continue pressing the brake, our distance traveled is going to become less until we reach this moment, which is at t equals 10. And D is going to eventually be no idea, right? This is our final. Here we go. This is what this looks like. Right? Our speed is positive, but it is slowing down. So our curve ends up going like this. Okay, and then like this other part back here is just going to be, this is not a curve. Actually, it's steeper than that. No. Lose the sloppiness. So like that. Yeah, it's pretty close. It's doing that. Alright, so this line represents a constant speed. We're going to be traveling at the same speed, same speed. But then the second we change it, that's t equals 0, d equals 0, that's when we start slowing down. So we slam on the brakes. And we start, we're still traveling at a fast rate of speed, so our distance is increasing quickly. But then as the brake gets applied for longer and longer and longer, our distance increases more slowly. And then finally we stop. T equals 10. Okay. The distance that we want is this one right here. So then how do we do that without using calculus? Because calculus is super easy to do this. This is going to be
a free £10 bet when you bet £10 on Accas or Bet Builders on football this week. Betfair. Play different.
Opt-in and previous deposit required. Valid for 72 hours on football hackers or bet builders. Min combined odds of 1.5. T's and C's apply.
D equals 1 half AT squared, where A is going to be a negative number, plus our initial velocity times time. Our initial distance is going to be 0. So d sub I is equal to 0. So that term is just going to be plus, right, plus 0. Okay. This one here is going to be looking at a transformed version of this one here. It's going to be the exact same thing, but it is reflected and moved around a little bit. Okay, so if we take that parabola, it's going to be the same parabola, just in a different orientation as this one over here. It's still going to be, right, a t distance of 10, and it's still going to be all that, it's going to still be the same curve because the acceleration is the same. But it's going to be a positive acceleration because we're looking at a deceleration value rather than the positive or negative value that we get over there. So, if you don't believe me, right, we can always look at both of these and see what's going to happen. So in this case, what we want is our distance is going to be equal to 1/2 times 6.6 feet per second squared times seconds squared is 10 squared. Right, so d is equal to 1/2 times 6.6 is going to be 3.3 times 100, or 10 squared is 100. So this is 330 feet. Okay, in this case, what we're looking at is d is equal to 1/2 times a negative 6.6 times 10 squared. Again, we're still taking that point up there, which is our vertex of the parabola. Okay, plus v initial. The initial velocity was 45 miles per hour times 10. Why don't I trust this? Yeah, just looking at it doesn't seem like it's coming out to be the same value. But negative 3.3 times 100 is still going to be, but this time it's a negative 330 plus 450. Nah, that doesn't come out to be the right. Okay, this should be the same value. Which means that that second one should be 660. But huh. Well, that didn't work. Okay, let's look at this a little bit differently. So if I'm doing this with calculus, then I'm saying that the derivative of the velocity, or derivative of the distance is going to be 2 times 1/2 is 1, a times t to the first. This was 22 fifths. Oh. Times 10. Which is 44. Interesting. And that's feet per second. Huh. Those are not the same number. Wait. Oh, no, 33. Yeah, that's definitely not right. Because this is saying this is going to be 66 feet per feet. That was miles an hour. That's my problem. Bingo. Okay, so 45 is not correct. That's miles an hour. Just erase it. That's why it's 660. Okay. 45 miles per hour times we had our conversion factor, which was 22 fifteenths. Yeah. Right, 45 over 15 is going to be 3 over 1, which is 66 feet per second. Excellent. That is exactly what I wanted to see, because 660 plus negative 330 is going to be positive 330. Right. So there's a couple of feet. There's a couple of reasons why this is actually interesting and important. Due to the fact that we're going up to the vertex of the parabola, we're going to get something that is symmetric on both sides. So it is half of the parabola. And so when we look at something that's like, oh, 1/2 at squared plus v0t or vit, then we end up getting 2 bits, which are half the parabola. Sorry, we get a full version of the parabola at v sub it. And then if we take this negative part here, the 1/2 at squared, again, we're going to get half the value. If we end up going all the way over to the other side, which would be at t equals 20, right, we get the other half of the parabola. This side would end up being 132. And this stuff would end up being at 20 squared is 400, half of which is 200. We're going to double 6.6, multiply it by 100, and we end up getting negative 132 entirely. These two things divide out, or sorry, double that amount, so 1320. We end up getting 1320 on both parts, so they just kind of go away. Anyway, feet per second. Watch your units. Okay. Let's pause those and do a couple of the differential equations things that we saw in Discord. So, solve system of equations. No, not that one. Okay, so this is in, looks like Portuguese. Also looks like it might be part of an exam. So maybe we'll change it just a little. No, I'm not going to do both. Okay. Whoa. What do you mean it's a different resolution? How dare you? So 1 point. Determine a solução do sistema Q dot P dot given here com condições iniciais Q of 0 P of 0 are 1 1 and considere o sistema now homogeneous Q dot P dot given here with a cosine in there. Woo! Ever so slightly different than the other one. That's mean. You should really use the same one as the homogeneous. Right, and this is non-homogeneous or not homogeneous. Solução com condições iniciais Q0, P0 are 0, 0. I guess. That's really mean. Literally, so as an educator, right? Okay, so make the homogeneous solution the same for at least one question, because at least the students will know that they will get that one, like half of it correct. Because they can be like, ah, well, you know, since I got the homogeneous solution and it's this, then they're going to be the same. Alright, so I am going to be ever so slightly mean here, in that I am only going to do one of them. And namely, here's the thing. I'm only going to do the first one. In that, in fact, I will do neither of them 100% identical to what we have here. Okay, so here's the thing, right? We're going to change this system to be Q dot is equal to negative 2Q plus P, and P dot is going to be equal to Q plus P. Okay? Neither of them are going to be 100% the same. Plus cosine t. Alright, because I'm mean. Where Q of 0, P of 0 is going to be 1, 1.
No internet, no worries. With
And in fact, right, we'll do
the songs that move you and take them offline wherever.
sine of t, because I'm mean.
Cancel anytime. Tap the banner to learn more.
Okay. I like it. Okay. So what we have is some x vector, which is going to be equal to a times. All right, that's our a. No, sorry, x vector dot. X vector dotted is equal to a times our x vector. Famished, yes. Where are ya? Ah, pens, pens. That's my problem. I went to the wrong. Wrong. Okay, so you're going to factor by grouping. Copy image. Paste image. Excellent. I'm on the wrong function. There we go. Alright, there we go. Alright, so to factor these two things, what we're going to do is we're going to take this, and we're going to take this as two separate groups of things. Yeah, sure. Now, why do I dot this? Reason is that if this thing here is a negative, I do not want you to factor that out, right? Don't factor out a negative. What you should do, or if you factor out the negative, then make sure that you also change the other sign as well, because factoring out the negative is going to switch all of the signs inside those parentheses. So when you multiply it back through, you're going to get a negative 6xy and a plus 27y. So just... No. I'm saying if there is a negative, right? If there is a negative in front of the 6xy, I don't want you to put parentheses there, because if you do, then that means you're pulling out that negative. So that means you need to switch the negative, or switch the sign on the inside. So, my point was, why am I putting like dotted parentheses around this thing, right? We're just grouping the two sections, and in fact, I don't even do this. I don't know why I did that. Right? What I do is I say, here's my first group, here's my second group. That's what I always do. I don't know why. To be fair, I haven't done it in a year, so. Alright, so first group. What we want is the greatest common factor of each of these things. So what do we get for our greatest common factor in each group? Go for it. Now we wait for the 10-second delay. Hope it's not 20. 5x. Sounds good. And then, once you got both of those, what's left? Other way around, but yes. Right, we're taking out the 5 as a factor of 10. So what we do is we say, okay, 10 is made up of, right, a 2 and a 5. We're taking that 5 away and putting it out here. The 45 is made up of a 5 and, right, a 9. So then what's left? Okay, you took, when we look at the x's, right, let's keep in mind this is x to the first power attached to the 45, and x to the second power attached to the 10. So then here, yeah, it's all good. So here you say, how many x's can we remove from both of them? How many x's are we able to remove from both of them? So here with our GCF, you didn't really say it, but what you said is that there's only one x that we can take from both. Yeah, divisors and dividends. Okay, so in this case, right, we're taking out the 5 as a factor from each of these things, which is leaving behind, right, those remaining pieces. So we took the 5 out, made it a part of the 5x out front, and now we're left with a 2 in the first position and a 9 in the second position. Right, and then if we take an x from both pieces, how many x's are left and where? I prefer to think of it all together. So from the 10x squared, we remove a 5x as a factor, so multiplicative, right? That 5x comes out front here, and then what's left behind? We remove a 5 from the 10, we're left with a 2 as a factor. Yes. So you are, when you factor out something as a multiple, then what we're looking at is, or as a factor, then you're taking that number of things away from that pile. So yeah, you had 2 in the pile, because x squared could also be written as x times x. Right, let's zoom in a little bit there. Nope. Right? So x squared is really x times x. So then what we can do here is we say, okay, same thing as before. This x comes out, and then this x is left behind. Over here, the 45x, this x needs to be taken out as a factor, and there aren't any left behind. So what does that mean? It's x raised to the 0 power and x to the 0 is what? Yeah, I mean, it's something to just get used to over time. Yep. So x to the 0 is just 1. There are none left behind. No x's left behind. But that doesn't mean there's nothing left behind, right? It means that there's a 1 there. It has to be left behind as a placeholder. Now, we don't care because it's multiplied by that 9, which is already staying behind. Right? But 9 times 1 is just 9. So we don't write the 1 in place of the x's. Right, so then up top there again, our 40 or our 10x squared, one of the x's gets used up by taking it out, and then this x here is going to get dropped because it's left. It got left behind. So 2x. Then the thing that goes in between them is just whatever operation was there, right? So since we took out a positive 5x, then nothing changes in terms of its sign. It stays as the same. Looks complicated. It isn't really. It's just a matter of getting used to it, you know, just doing it over and over again. All right, how about the GCF for the second set? Here's the other thing, right? Me personally, I'm going to take that sign that's between them, and I'm going to put that right there. 21, lol. Okay, you got a 3. It's also positive. And here's the other thing, right? Whatever that sign is that's between, not only is that going to just come down here and be the sign between these two things, but also I'm going to use that as the GCF sign. All right, important. We'll see why in a minute. One of the #1 things that students would leave out is this thing, the sign that goes between them, and that's a big problem. All right, we'll see why in a sec. Okay, is there anything else that's common? Yeah, see, I'm used to it. Blue. No, yellow. The XY. Right. Yep, there's only one X in there. So, just Y. Yep. So we have the 3, which goes from both of those 6 and 27. And we have a Y, which comes from both 6xy and 27y. So now that we have both of those parts, right, we look at this and we say, okay, the GCF was 3y. So if we remove, again, as a factor, 6 breaks up into 3 and 2, so we leave behind. Let's maybe jump it all together, right? If we take out a 3y from 6xy, what's left behind? All right, 3 minutes to ad break. Okay, so if we multiply that back in, 3y times 2 is going to be 6y. So if we remultiply our GCF times whatever we leave behind, we should always get back the thing that's on the inside. So again, if we multiply our 2 by our 3y, we're going to get 6y. Yep. So what's going on? Hang on, we're not done with the other part yet. We'll get to that eventually. Right, so we have an inconsistency at the moment. We started with 6xy, and now if we were to remultiply the 3y in, we just get 6y. So 20 seconds, how do we fix that? Oh no! Alright, we'll be right back after ad break. Perfect timing. All right. Thank you, everybody, for sticking around through the ad break or lurking. Always appreciate lurkers. Twitch is often run off of lurkers, so join a whole bunch of channels and turn their volumes like down really low to like 1%. If you got the bandwidth. If you don't do that. Okay, so we do get the +9 at the end here, but here's the thing. If you just do 2 and +9, then you should be able to take those things and combine them and make 11, right? But then if we re-multiply everything out, 11 times 3y is just 33y. So what happened? We didn't start with 33y, so we can't end with 33y in here. Yeah, no worries. Which variable? Might be a little nicer to see this a little cleaner, right? If the greatest common factor is 3y, then what do we take out? Right, the 3 gets taken out from the 6, and the y gets taken out from the y. Right? The 2 is left over because 3 removed as a factor from 6 is going to leave behind a 2. The y is going to remove the y because you're factoring that out. What's left? So not exactly. That plus belongs here, not on what you just drew out. Yeah, I know it's supposed to be plus. That's fine. But again, so first of all, you got a problem with, again, the plus between what you wrote doesn't actually belong there. I'm saying it's essential where I'm writing it, in the middle of this section, because we're adding two separate things together, right? The 5x times the 2x plus 9, and the 3y times that parenthetical that's there. Okay, but the one that's between your two is saying that we would add these things together, which is not actually true. That's okay. We'll get there. So I've got earlier problems than that. So one more time, right here, right? GCF is 3y of those last two things. When we take out the 3y from 6xy, what is left behind? The 3 took a factor of 3 from 6, leaving behind a 2. The y took out the y, leaving behind a 1, but again, 2 times 1 is just 1, so, wow, no. 2 times 1 is just 2. It's almost 1 o'clock here, it's fine. 2 times 1 is just 2, so we ignore the 1 for the moment. What's left behind in that whole term? Bingo. Yep. 2x. The x got left behind because nobody ever touched it. Right? And that's something you do have to watch out for, right? Is that you might end up having a term that you just kind of ignore because you didn't touch it. But just always remember what's being affected by our GCF being taken out, and then look at every single term going in through every factor of it and determine, is this being affected at all by the GCF leaving? In the case of our 6, right, the 3 got taken out, so 2 is left behind. 3 times 2 is going to be 6. If we re-multiply, we're not going to do it. Just in your head, think like, okay, if I were to redistribute the 3y to the 2x, what do I get? 3 times 2 is 6. Cool. Add that up here. We have an x and we have a y, so 6xy. Good, that's where we started. So my factorization of taking a 3y out from that stuff and then leaving behind 2x is going to be equivalent. Right? So 3y times 2x is equivalent to 6xy from up there. Good. Then we say, is that the same for 3y being taken from 27y, right? We take the 3 from the 27, we're left with 9. We take the y from the y, we're left with 1. 9 times 1 is just 9 again. Yeah, I got you. Okay. Now, what's also really important about these factors, or the stuff that's left behind? Definitely go for it. Oh. Mm-mm-mm. Can we? Shouldn't be. No, I am teasing just a little bit, so. All right, now what do we have here? Let's rewrite this because that looks sloppy. Right, what do we have here? Okay. So anytime that we do factor by grouping, which is what we were looking at here, we separate into two groups and we say, okay, let's do a GCF factor from each part. So the first part, again, 10x squared plus 45x, we said there is a factor of 5x in both of those terms. Cool. So that comes out, 5x, and then we're left behind with 2x plus 9. Second group, we find a GCF of 3y. We take that out, and we're left with 2x plus 9. What do you notice? Right. So reverse distribution is just the same as factoring. It's the exact same thing. So here, what we're doing is another GCF factoring. But this time it's a GCF factoring of the binomial that we had left behind in both parts. So here, we say, hey, look at that. We got the same binomial on both of these. So that can come out front and be 2x plus 9. Then what we have is a secondary group which is multiplied by the stuff that was left behind. And the stuff that was left behind is a 5x plus a 3y. That's the way to do that one as far as I'm concerned. Now, I did change the order in which they're multiplied. So if that matters, right, if it matters which order you multiply stuff, then you just need to watch yourself. But for regular real numbers, you never have to worry about the order in which we multiply stuff, because regular real numbers are what are called commutative. We can swap their order for multiplication, and we can swap their order for addition. And we always get the same stuff for them. Now, you want to see something fun? What would have happened if the question was factor 10x squared plus 6xy plus 45x plus 27y? Right? Same stuff, different order. Now, I very purposely picked these particular things in this particular order. If I move the x squared over with the y term, the 27y term, then you'd probably have a really hard time, because these binomials would no longer be the same thing. And so you'd have to look at it and say, okay, I can't do that based on this order. But if you shift stuff around a little bit and you say, let me get the most GCFs that I can. Let's see if we can get the most common stuff together. So in this case, right, we've got an x squared and an x. That's helpful. And we've just got numbers here. So I'd be hesitant on this one, because I'd be like, well, maybe it won't work. But in the original, right, we had an x squared and an x, and then we had a y and a y. So variable terms wise, we're factoring out GCFs on both terms. That seems promising. I like that. This other one down here, yeah, maybe it'll work, maybe it won't. You just have to go through it and try. So we look at this stuff and we say, okay, the first one's 10x squared, the second one is 6xy. We have an x in both terms. We also have a 10 and a 6. GCF on this one, greatest common factor, is going to be a 2. Right, so 2 and x. What's left behind? 2 from 10 leaves 5. X from x squared leaves x. 2 from 6 leaves a plus 3. X from xy leaves y. You should see it already. Plus 45 and 27. Again, none of the variables are going to come out as the GCF. Oh well. Just the numbers. What's common between 45 and 27? Well, you might think, okay, 3 works, but that leaves a 15 and a 9. 15 and 9 also have a 3 in common, so that's another 3 that we take out. So 2 3s, 3 times 3, makes a 9. So we have a 9 in common. 9 from 45 leaves a 5x, plus 9 from 27y leaves a 3y. Right? And then we take out 5x plus 3y, and left behind was a 2x plus 9. Oh, look at that. And these are multiplied because what we want to do, if we want to reverse this, is again, we want to do like a distribution. Nope. Right, we multiply these, we get a 10x squared, we would get a 45x, we would get a 6xy, and we would get a 27y. So if we multiply all this stuff out, we end up with the exact terms that we started with at the top. Right, and that's going to be important. That's to make sure that we reverse to get the exact same stuff we started with. That's going to be really helpful. Now, could do one more. I think this is still, yeah, good. Just move this over here. Let's bring this down. What if this was 10x squared minus 45x minus 6xy plus 27y. Now I very intentionally picked these two. What are you doing? Okay. My mouse was trying to take control. Okay, so same GCF between these things, really, right? We've got the same 5x on both of these terms. And here we have the same 3y on both of these terms. However, I'm going to recommend that you take this negative down and make it a minus 3y. Now, why on earth would I do that? Right? If you make it 5x here, we still get left with a 2x plus 2x minus 9 in this case, because again 5x out of negative 45x is going to leave a negative 9 behind. If we had this be plus here, then a 3y out of 6xy is still, as we had above, a 2... sorry, messed up. Okay, a 3y taken out of negative 6xy is going to leave behind a negative 2x. And then a 3y taken from 27y is going to leave a positive 9. And now here, again, you should notice that this and this are not the same. But they're really close. Right? They are actually off just by a sign switch. And not just any sign switch, a sign switch on both terms. So what does that mean? Well, that means if we want to switch the sign on the inside, make it a positive 2x and a negative 9, then we just switch the sign on the outside and make it a negative 3y. So make that thing that is your sign in between a part of your GCF, no matter what it is. Right? The sign between them should end up being part of the GCF. And if it's part of the GCF, it's also going to be taken out, which means that it's going to change the other signs that are there. Okay, then here, common factor, 2x minus 9. Left over, 5x minus 3y. Right, and you can play around with these and try to figure out, like, if, well, if there's a pattern. you could try to figure out what the pattern is and whether or not something is changeable to become a good pattern. So again, here, this worked out very nicely. Having the 10x squared minus 45x minus 6xy plus 27y worked. We got the same GCF remains, which are going to be the next greatest common factor for our binomial factorization. Right, it doesn't matter how complicated the binomial ends up being, or if it's even larger than a binomial. It could very well end up being a trinomial or a larger polynomial. But anyway, play around with it, see what you get for each of these individual terms, and where the signs are allowed to be, basically. I think I might have had another thought at some point, and now I don't remember what it is. That's weird. Anyway. Hey Don, how's it going? So Famish, the other thing that you're going to definitely come across very soon is what happens when you have trinomials and you're trying to factor stuff like that. Gotta tell you, it's not gonna change anything. It's gonna change like how you approach the problem, but it's not gonna change the difficulty of it really any at all. As soon as you realize like what's going on and oh, this is just factoring by grouping again. You just have to make a little tweak to it and then it ends up being the same problem. Yeah, we're doing pretty well. I was just about to attempt the problems that Mataratos had put in to Zach's Discord. Since it's differential equations, hell yeah. All right. So, if Mataratos has come over, hi, my name's Obi-Wan Pez, this is N Simplex Pachinko, and I have altered your problem to be not quite the same as the ones you gave us. So, you can yell at me for that, but that's fine. So the basic idea here is that we've got a system of differential equations that look, roughly speaking, like this. We've got x prime is going to be equal to a times your x vector. A is your transformation matrix. X is the x vector that you're looking for. And then we have a plus f of t vector, which is going to be all of the non-homogeneous portions. So, I'm answering both of your questions at once, but they're slightly different. Okay, so 1. We have to start with x homogeneous. So in order to find your homogeneous x vector, the way that we're going to set this up is we're going to say that the x dot homogeneous was equal to a times x homogeneous. Right? There is no f of t as a part of this. So how did that work? Well, we end up with, again, x homogeneous vector prime is equal to, the way you had it here, or sorry, the way that I rewrote the problem here, right? We're going to take the homogeneous portion and say this is going to get us -2, 1, 1, 2. Times, nope, times x homogeneous vector. Right, and the way that we look at this is that this is going to be the same as a constant times our x homogeneous vector. Right, so we want to see when exactly we're going to end up with our A transformation getting us a linear scaling, or scaling by a constant. Okay, so the way to do that, again, we're going to bring this over there. We're going to end up with A x homogeneous minus lambda x homogeneous equals a 0 vector. And the way we make that happen, again, this is a right multiplication of x homogeneous vector, a minus lambda, but you can't just subtract a and a lambda, which is a scalar, so we need to have something that is the same sized vector. So this is going to be our I vector, I matrix of the same dimensions as A. Right, so however big A is, I is the same size. And that has to be equal to our 0 vector. So in this particular case, that then means we have, better way to think about it, hang on. This means that the A minus lambda I needs to be equal to our 0 vector, because homogeneous vector can't be 0. Right? If it is 0, it's boring. We don't like that. All right, this then means that the determinant of A minus lambda I must be equal to 0. Right, the determinant of that particular subtraction must be 0 in order for A minus lambda I to be equal to a 0 vector. All right, so with this means that we take our A vector, determinant. Our A vector is -2, 1, 1, 2, and then we have to subtract lambda from its diagonal. That's set equal to 0. For anybody who does not know Don, he does math. And was playing some DayZ tonight. Awesome. I remembered seeing that, and it's kind of like your game, so. How'd it go? Alright, so our determinant here is going to be the main diagonal multiplied by, or no, multiplied together, and then subtract the off-diagonal product. So our main diagonal product is going to be -2 minus lambda times 2 minus lambda, okay, minus 1 by 1. That still needs to be equal to 0. So here, we go and take the first set and we multiply them out. We end up with a positive lambda squared, a positive 2 lambda, and a negative 2 lambda, so that's going to be plus 0 lambda. We don't really need to do that, but whatever. And minus 2 times 2 is 4, minus 1. Oh, so close. Too much. Alright, so lambda squared minus 5 is equal to 0, therefore lambda squared is equal to 5, therefore absolute value of lambda is equal to the square root of 5, and therefore lambda can be either plus or minus square root of 5. Only slightly inconvenient, it's fine. Got a decent amount of kills? Nice. Yeah, there's another community goal up in Elite Dangerous, so now I gotta go check that out later. And I completed a pirate settlement. It's just like a criminal hold, so like there are now huge amounts of conflict zones that you can just like pop in, and there's pirates there, so you just blast them, and you can make a fairly decent amount of money. And then I started construction of a government site, which is going to like boost a whole bunch of stuff. So criminal site next to a government site. It's fine. This is fine. But it boosts the security, brings it back up to a normal amount, so it's not going to be like, oh no, we have to go into a lockdown phase, which kills the entire like point of stuff. Point of doing anything, basically. But it boosts the quality of life in the system by a huge amount, and then boosts some other stuff by a small amount. So, and in my first system, I've got like still 5 open projects. Every time I complete one, I just keep adding more, and then 2 more systems opened up, and I completed one of them with a small thing. No, wait. Yeah. Okay. In my secondary, so in my primary system, I have 5 open items. My secondary system, I have 1 open thing, but there's like no end to it. So you just like, whenever you get it done, you get it done. It's fine. Same with the primary. The tertiary system is the pirate system, which now I'm adding a governmental site. And then the quaternary system, whatever it is, has a time limit on it. So I have 3 weeks to complete this one, which is, again, I made it small, but there's like 5 or 6 sites that I can work on. And once I complete the one that's, so it's a triple star system, I think. So once I complete the settlement site around the primary, then all the rest of them open up, and you can just do them whenever, right? The time limit's over. You have to do the primary site within 4 weeks. That's the only rule. If you don't do it within 4 weeks, it releases your... I've got a spreadsheet. Of course I do. So I wasn't really planning on... Yep. I wasn't really planning on adding like so many new systems. but other people have either dropped them or let them expire. So I was like, I'll take that one. Yep, I'll take that one. It was originally just the two that I had, the primary and secondary, and then the tertiary became available, and then the quaternary became available, and I'm just like, yes, I will take them. So now I've got like a clump of 4 star systems which have my name on it. Hell yeah, I can't let them go to waste. So later on, I'm gonna like go to one of those systems and then colonize from them. It keeps adding these systems to Commander Psyche, who's one of my other Twitch, she's a Twitch ambassador actually, so it's pretty awesome, and a Elite Dangerous partner, or at least has been an Elite Dangerous partner in the past. So it's pretty cool. It like keeps adding them onto her company. So like our fleet is controlling them, and so it's like, oh well, you know, if our fleet keeps controlling more and more systems, first of all, it's like a distraction and can keep a lot of other people busy who are trying to hurt our corporation. They try. And there's, I don't know, there's a bunch of other stuff that's going on in the background, but Mataratos, if you're watching this, I apologize. You don't need to hear about Elite Dangerous. Yeah, so when you get it above a certain level, if your company influences a particular system over 75%, then your company ends up going into an expansion state, and you will take over a slot that's available in one that's within like 15 light years. And it's random. You don't get to decide, or at least I don't think you get to decide how it expands, which is too bad, but it's alright. Alright, so what we're doing here is we're going to take our eigenvalue, which we found, lambda, and we're going to do plus root 5 first. We're going to do minus 2 minus root 5, 1, 1, 2 minus root 5. And this needs to be taken as a system, as a matrix system, of now a minus lambda 1I is equal to, times our x homogeneous vector needs to be equal to our 0 vector. So we go back a few steps here, and we say that this line has to be true, still. Nope, not that one, that one. Right, this has to be true. And again, we know that x homogeneous vector is not 0, so then what we want to do is find possible vectors x which make this true. So for what vectors do we get that our a times x homogeneous is going to get us the same thing as our lambda times homogeneous? So we're going to augment this matrix with 0, 0. And here's the other thing, right? So we have been working for over 5 years, like since I joined the corporation, to try and move her corporation's control down to a site where they gave her, because she was a Elite Dangerous partner, they gave her a named ground settlement, which back then was unheard of. It was amazing. And they named it after her think she might have applied, but they named it after her kitten who had passed. So his name was Zero, after Zero Cool from, yes, hackers. We're going to do row 1 times... That's a terrible idea. Let's do... Yep. So they got her one of those laser cut things that's like the glycerin block that's got like the white etching in it with the ground settlement picture and then Zero's Rest underneath it established what date it was. So it wasn't just her. It was like all of the elite partners got a ground settlement. And so they gave that to her, and she absolutely cried on stream. It was amazing. So we've been trying to push her corporation in that direction, and it's been impossible because, you know, you get a random location within 15 light years of where you were, so you might end up going completely opposite directions. So we let those other ones go, let other people take them, and keep trying to push down, and every time we moved in the correct direction, we'd focus on that one, push it up to 75%, and then make it jump another one, and then push that one. So it was 5 years, and we hadn't even made it halfway. And then colonization opened, and several of the people who were on our in our corporation like jumped settlements as close as they could to this thing, and they ended up getting like 4 different settlements right around the proper system. And then the people who were there already were like, whoa, what are you guys doing? We're like, hi, just passing through, don't worry. We just want this one. Alright, so R2 multiplied by a positive version of the one that's up there. So 2 plus root 5 plus row 1 put back in R2. Now when we do this, this ends up being 0, 0, 0 going across the bottom. I know. And then again, just for shits and giggles, they were like, it's no problem. Just here you go. Okay, so just to make sure, right? 2 minus root 5 times 2 plus root 5 is going to be 4 minus 2 root 5 plus 2 root 5 minus square root of 5 squared is 5. Okay, plus 1 from row 1 is going to be 0. Cool. Made sure that that worked. Alright, and then this is still going to be negative 2 minus root 5. We don't have to change anything, because what we do here is we say, oh look, our first row here is going to be negative 2 minus root 5 times x1 plus x2 equals 0. We can just shift x1 over to the other side, and x2 is equal to 2 plus root 5 times x1. Which means that we can let C plus. In this case, because our eigenvalues are the same, but they're just opposite sides of the spectrum here, one positive, one negative, we could just put that as our subscript. So our xi plus vector is going to be, right, let x1 equal 1. And x2 is going to be 2 plus root 5. Woo! Okay, and then we do the same thing. Now for lambda 2, which is negative root 5. Which is going to get us negative 2 minus negative root 5. 1, 1. 2 minus negative root 5. And then that's going to be augmented with 0, 0 again. So with this being negative 2 plus root 5, and this one being 2 plus root 5, again, what we can do is the exact same operations as what we did back in the other one. We're going to do R2 times the number that's up there, so negative 2 plus root... Oh, no, wait, we switched the signs. So let's switch those signs. Positive 2 minus root 5 times row 2, which is 1 in that first column, plus row 1, store back to row 2. So here we get a 2 minus root 5 times 1 plus negative 2 plus root 5 is going to be 0. 2 plus root 5 times 2 minus root 5 is going to be 4 minus 5 plus 1 is going to be 0, so that's gone too. Cool. So negative 2 plus root 5, 1, 0, 0, 0, 0. Right, so again, this is going to be negative 2 plus root 5 times x1 plus x2 is equal to 0. So x2 is equal to plus 2 minus root 5 x1. Let x1 be equal to 1, and therefore xi2, or xi negative, is going to be equal to 1, 2 minus root 5. Right. So, the solution, x homogeneous, is going to be, and I forgot that this was only the first, like, half the problem, is going to be equal to, okay, a linear combination of xi1, so in this case, let that be positive, 1, 2 plus root 5, times e raised to the lambda 1, in this case lambda positive, is root 5 t, plus c2, 1, 2 minus root 5, e to the negative root 5 t. 2 minus root 5, cool, negative root 5 t. Yep. Okay. So that, again, is our homogeneous version. So if we take the derivative of this, we should always end up being able to add it to taking its derivative should always be the same as multiplying a way up there times this stuff. Alright, you could do it out if you want. Check it. I'm not going to. Okay, so then we need to add our sine t into the second position. So, X general is, wait, hang on. Prime. Has to be equal to. A times. Now, in this, we could make it homogeneous plus our generic. Because if we do that, oh no, ads. Three minutes. Sorry, everybody.
The Virgin Atlantic holiday sale is now on. This is your sign to taste Jamaican jerk chicken so good it brings a tear to your eye. Catch a New York basement gig worth the 10-block detour. Or hit the dunes in Dubai and find sand in your pockets for weeks. Seize the sale. Tap the banner to book now. Selected routes. For T's and C's, visit virginatlantic.com.
Calling all spinners. Join Sky Vegas, the online casino, where we offer new players 50 free spins to use in your first 7 days, and 200 more when you deposit and spend £10 within 30 days, all with no wagering required. You love a good spin? We love a good spin. Sky Vegas. Play. It's why we're here. 18 plus free spins loaded on first eligible game. Game and eligibility restrictions and further T's and C's apply. BeGambleAware.org. This is an ad by BetterHelp. In a recent survey, 75% of Brits said they feel anxious or on edge, and many avoid discussing mental health for fear of judgment. But by staying silent, we can't get support, and that affects everyone. At BetterHelp, we have over 10 years of experience matching people with the right therapist. Because we're all better with help. Visit betterhelp.com/Spotify Music for 10% off your first month. That's betterhelp.com/Spotify Music.
Oh, whoops. I missed a part. That's what I forgot. Plus FFT. Kind of important. Alright. Plus FFT vector. Hey, famished. So we're going to subtract off our null space solution. So our x prime vector being equal to a times our x prime vector, or x vector, we're going to subtract that off. Again, that's our homogeneous solution or the null space solution, so that's gone. Now we've got x sub g vector prime is equal to a times x sub g plus f vector of t. Okay. What on earth is that? That feels wrong. Alright, I do not want to do Jordan form. Because as much fun as that is. Or matrix diagonalization. Everyone loves lurking. Huh. That, ironically, might be the better way to go. I hate it. Because I can't find my notes on... no, it's getting into Jacobian stuff. I don't want to do that. That's nonsense. Alright, hang on. Then quiz time. Nice. Alright, we're going to have to do the diagonalized version. Which, pain in the rear, but it's fine. No, I was looking at the... actually, when we did the ODE course here on Twitch, I did diagonalization, I did undetermined coefficients, and I also did... no, the other one, variation of parameters. So we did all of them, but I don't have my notes available for that immediately, so we're just going to go with diagonalization method. Okay, so let's let x sub g be equal to t matrix times a y vector, where t is an appended eigenvector matrix. So in this particular case, we're taking both of the eigenvectors and we're sticking them next to each other. So this was 1 and 1. And it doesn't matter in what order we go. So 2 plus root 5, 2 minus root 5 is what we've got. So, if we plug this back in up above, what we've got is our, nope, hang on. X sub g prime is going to be t times y vector prime, which is equal to a times t times y vector plus f of t. Okay, now t is constants. That's all it is. So t gets out of this whole derivative thing completely unscathed. On the other hand, we've got now a y prime vector which we need to solve for. Well, that's somewhat inconvenient, isn't it? Not really, it's okay. Then we get a times t, and I'm going to associate these two constant matrices with each other, and then we have our y vector plus f vector of t. I now want to get rid of the t that's there. As a vector, or no, as a matrix, we need to multiply by the t inverse matrix on the left. And this is very important because matrices are not commutative, or at least not necessarily commutative. So multiply by t inverse on the left of this group of terms, at y vector, and also on the left of f of t. So we have to multiply on the left-hand side to all these things. Now, because it's a matrix inverse, T inverse times T is going to be the I matrix, the identity matrix of the appropriate size. Here, again, 2 by 2. Y prime vector is equal to. I am now going to associate T inverse A T altogether times our y vector plus T inverse times our f vector. Now the identity matrix is just still going to be, in this case, we multiply it, it doesn't change anything. So it's just going to be that. Okay, now, here's the weird part. Phobos! Good evening and welcome everybody. My name is Obi-Wan Pez and this is Ensimplex Pachinko. We are currently, ahoy to you as well. We are currently working on some non-homogeneous matrix systems differential of equation, system of differential equations. There we go. So right now we're working through the diagonalization method. We're just getting to the diagonalization part. So here, D is a diagonalized matrix with the respective eigenvalues in those particular locations, and zeros elsewhere. Were you working on systems tonight? If anybody has not yet followed Phobos Stream, please do so. She is an awesome mathematics streamer. Just regular ODs? That's all good. You cuss and judge people. Excellent. Only the people who deserve judging. Actually, come to think of it. Did you do a thing? No. Okay. Nope. Okay. Never mind. If you cross your GitHub. Oh no. I'll flood the chat with other stuff later. So if anybody has not done so yet, in addition to Phobos and Dawn, we also have Pen Center's Discord server is kind of like our central repository for everybody in the Elements crew. So if you feel like stopping by and interacting with a bunch of us, a lot of us are in there at various times. Most of us have our own Discord servers, and those can be found on our individual, or you can go to each of our individual Twitch pages and interact with us and find out what the Discords are. I don't have my own Discord, or rather I do, but it's just for like me and my 5 friends who do gaming, and we call each other by our real names. The real reason why I haven't let you all in there. Okay, so now y prime is going to be equal to the diagonalized matrix, which is this root 5, 0, 0, negative root 5 thing, plus, that way, plus the t inverse matrix times f of t. So, now we can actually, like, set this up and put in the actual values to try and see if we can come up with something nice. So, first of all, t inverse here is going to be 1 over the determinant of t multiplied by a slightly different matrix. So this is, what is it? You change the main diagonal, and you make the off diagonal negative. Hope that's right. Yep. Not bad for not having done that in a long time. Okay, and the determinant of t is equal to, this is going to be multiply, get your product of the main diagonal, so this is going to be 2 minus root 5. And then we're going to subtract, parentheses, the product of the main diagonal, which is 2 plus root 5. Okay, yeah. Worried me for a second there. This is going to be negative 2 root 5, right? Because when we bring this in, we get a negative 2, which then subtracts out from our 2, we get 0, and then negative times root 5 is negative root 5, plus another negative root 5. It's going to be negative 2 root 5. Alright, so that is our determinant of t, and therefore t inverse is going to be equal to 1 over negative 2 root 5 u multiplied by the matrix 2 minus root 5, negative 1, negative 2 minus root 5, 1. Alright, we'll let all of this work out automatically. Okay, so y prime is going to be equal to, this is now root 5, 0, 0, negative root 5, plus, this was now a, let's do negative, it's fine, so minus 1 over 2 root 5 multiplied by, whoa!
GOtEL.
Phobos, oh my goodness, thank you. I gotta change some of those alerts and stuff. Right, and then we'll just, I'll just copy paste this, it's fine. Copy paste and bring that over there. Clear that one, and then go like that. Bring this over there. Okay, now this is multiplied by, and I never actually wrote this before, but it is f. F in this case is 0, and then sine of t at the bottom. Oh, and I forgot why. Of course I did. Okay, and it's fine. Times y vector. Okay. So this cool is, I think, a large group of separable differential equations. Could be wrong, but or it's solvable by using, probably is solvable using, who is it? Variation of parameters. So actually, non-homogeneous linear systems of differential equations. Excellent. This is out of LibreText. Hey, it worked. I'm actually kind of shocked. So if anybody wants to follow along with this LibreText, we are, let's see, the one that's most similar. Pretty much any of them will work. Hmm. This version might have been easier. Kramer's rule. Okay. Probably is. Out of curiosity, right? What other ways did they use to solve this? Oh, William F. Trench. That's exactly the same one I used. Variation of parameters for non-homogeneous linear systems. Yeah, that's the same thing. Okay. So let's go through and make sure we've got it. Linearly independent solutions. Fundamental matrix. Ah, okay. Oh my goodness. I don't remember how we did this. Let's try again. No, that's the right one. Hmm. Okay. Oh, we can't do it by undetermined coefficients because we don't have the same stuff. Maybe we can. All right, let's actually shift. Let x sub g be equal to some a vector, which is constant, multiplied by sine of t, plus some b vector, multiplied by some cosine of t. Okay, so x prime sub g is going to be equal to a vector is no different times cosine of t minus b vector times sine of t. Okay. So this says that our a vector times cosine of t minus b vector times sine of t is going to be equal to a, just a reminder, right, is negative 2, 1, 1, 2, right? Negative 2, 1, 1, 2. Cool. Okay. Negative 2, 1, 1, 2. Multiply by a vector sine of t plus b vector cosine of t plus g, which was 0, 1 sine of t. Alright, so this is going to get a little tricky, but we got this. So we're going to get a1, a2 for cosine of t. Alright, plus negative b1, negative b2 for sine of t equals negative 2 plus negative 2a1 plus a2. This is sine of t. Bottom is going to be a1 plus 2a2 plus cosine of t is going to get the same exact thing but with b's. So negative 2b1 plus b2, b1 plus 2b2 cosine of t plus 1 sine of t is going to go over to here. So mark that. Makes that 1 there. Now, set both sides equal such that we have functions. Yeah. Right, so for cosine of t, we have a1 is equal to negative 2b1 plus b2. A2 is equal to b1 plus 2b2. For sine of t, 4 equations, 4 unknowns. I'm liking it so far. Nope, not equal. For sine of t, we have negative b1 is equal to negative 2a1 plus a2. For negative b2, we have a1 plus 2a2 plus 1. Okay. Also, just real quick, if anyone does want to donate to GOtEL, we have direct link here, which is also tax deductible if it's within the appropriate whatever range. So if you are sending any money directly to GOtEL, that's the place to do it. Phobos, I'm gonna take those 700 bits and convert it to cash and donate it in your name from my end. So but thank you very much. Okay. So how do we do it, huh? So how are these related to each other? Okay, so we can make a matrix out of this, which is going to be A1 is 1, A2 is 0, just with the first equation coming from cosine. A2 is 0. B1 will be brought over to the other side and make a 2, and B2 will be brought to the other side to make a negative 1. Okay, so we're going to go A1, A2, B1, B2. Matrix system, right, equals 0. Second equation, dealing with A2 specifically, is going to be A1 is 0, A2 is 1, B1 is negative 1, and B2 is negative 2. Okay, this is going to be super awesome in terms of row reduced echelon form. Alright, so negative B1, let's bring B1 to the other side, right? So that, oh, sorry, that's also a 0. And another 0, and a negative 1 here. If we're going to bring B2 to the other side, We'll make a positive 1. Switch all the rest of the signs. It doesn't matter, right? It's all more or less the same. A1 is 2. A2 is negative 1. B1 is going to be negative 1. And B2 is going to be 0. Lastly, B1, no, A1 is negative 1. A2 is negative 2. B1 is 0. And B2 is going to be negative 1. Okay, double check. Alright, so here we get A1 plus 0 A2 plus 2B1 minus 1B2 is equal to 0. Okay, everything shifted over to the left. 0 A1 plus 1 A2, shift left, is minus 1B2 minus 2B2 is equal to 0. Shift left again. 2A1 minus 1A2 minus 1B1 plus 0B2 is equal to 0. And shift left again. Negative 1A1 minus 2A2 plus 0B1 minus 1B2 is equal to 1. Cool. So, the way we're going to do this, row reduce echelon form, we're going to do row 3 plus 2 row 4. Put back into row 3. Row 1 plus row 4, plug back into row 4. So 1, 0, 2, negative 1, augmented 0. 0, 1, negative 1, negative 2, augmented 0. Okay, 3 and 4 added together. So this is going to be 2 plus negative 2 is going to be 0. Negative 1 plus negative 4 is going to be negative 5. Negative 1 plus 0 is negative 1. And 0 plus negative 2 is going to be negative 2. Augmented with, this is going to be row 3 is 0 plus 2 row 4 is 2. So 2. Row 4, row 1 plus row 4 is going to be 0, negative 2, positive 2, negative 2, 1. Okay, so this is going to be row 4 plus 2 row 2. Row 3 plus 5 row 2. One, 2, negative 1, augment 0. 0, 1, negative 1, negative 2, augment 0. Okay. Row 3 plus 5 of the one above it is going to be 5 and negative 5 is 0. As expected. Negative 1 plus negative 5 is going to be negative 6. Negative 2 plus 5 negative 2s is going to be 6 negative 2s, or negative 12. Row 3 plus row 2 is going to give us a 2 there. This is a 0. Row 4 plus 2 row 2 is 0. Engineered that way. Oh, interesting. Row 4 plus 2 row 2 is going to also get us a 0. Uh-oh. No, we're okay. Row 4 plus 2 of those is going to be 3. Negative 2s is negative 6. Row 4 plus 0 up there is going to be 1. Okay, that's not too bad. Multiply by negative 1/6. Multiply by negative 1/6. Leave the other 2. One, 2, negative 1, augment 0. 0, 1, negative 1, negative 2, 0. 0, 0, 1, 2, negative 1/3. 0, 0, 0, 1, negative 1/6. Okay, row 3 minus 2 row 4. Row 2 plus row 3. That's going to clean that up nicely. Row 1 plus, nope, minus 2 row 3. Okay, so this is a 0, no, a 1, a 0. Row 1 minus 2 row 3s is going to be 2 minus 2 is 0. Okay, -1 minus 2 2's is going to be -5. Oop. Get that out of the way from my face. And then here, minus negative, it's going to be plus 2/3. Next, 0, 1. Row 2 plus row 3 is going to get us another 0, engineered that way. -2 plus 2 also happens to be 0. -2 plus root 3 is going to be -1/3. Okay, 0, 0, 1. Row 3 minus 2, row 4 is going to be also a 0 by engineering. And row 3 is -1/3 minus 2, so plus 2/6 is 1/3. So that should be 0. 0, 0, 0, 1, -1/6. And I think that's what it says. I'll do a row reduced echelon form after this. Do it on my calculator, do it fast. Alright, 1, 0, 0, 0. How do we get that? That's going to be row 1 plus 5, row 4. So 2/3 is 4/6. 4/6 plus -5/6 is going to be a -1/6. 0, 1, 0, 0, -1/3. 0, 0, 1, 0, 0. 0, 0, 0, 1, -1/6. I mean, this isn't really surprising. One of the terms being 0 doesn't do much. It just says that there isn't a sine or there isn't a cosine as part of our final thing. So, it's not that surprising. You know what? Let's just double check. Okay, row reduced echelon form of a, what kind of matrix is this? 4 by 5. We have 1, 0, 2, -1, 0. 0, 1, -1, -2, 0. 2, -1, -1, 0, 0. -1, -2, 0, -1, 1. Okay, and then we do math, row reduced echelon form of matrix A. Yep, -1/6, -1/3, 0, -1/6. Awesome. Alright, we did it right by hand. Woo! So what does that mean? Again, this is going to be B1, B2, no, jeez. A1, A2, B1, B2. So the G, no, F, no, that was part of the differential equation. The X general is going to be equal to, this was A1, A2, so -1/6, -1/3 sine t plus 0, -1/6 cosine of t. Awesome. Right. A sine, B cosine. A sine, B cosine. Cool. So that means that this big thing, right? The total particular solution involves all that stuff. Go down here and paste. Okay, and then we select all this stuff, and we copy and we paste. So our total X solution is going to be C1, 1, 2 plus root 5 times e to the root 5t plus C2, 1, 2 minus root 5 times e to the negative root 5t plus negative 1/6, negative 1/3 sine of t plus 0, negative 1/6 cosine of t. But we're not done, because we need the particular solution, which said that the two functions evaluated at 0 should give us 1, 1. So this is quite possibly going to completely crash and burn, but nonetheless. X at 0 should be 1, 1. Which gets us, right, C1, 1, 2 plus root 5 times e to the 0, so that's just 1, plus C2, 1, 2 minus root 5, e to the negative, nope, sorry, also times 1. Plus negative 1/6, negative 1/3 sine of 0, which is going to eliminate this whole term, plus 0, negative 1/6 times cosine of 0, which is 1. Okay, so we can actually add this to the other side and make it 1/7/6. It's going to be equal to C1 plus C2 2 plus root 5 C1 plus 2 minus root 5 C2. And now, quite frankly, we're going to do row reduce echelon form on my calculator again, because no. We're about done. Alright, 2 by 3. It's going to be 1 and 1 and 1. And the other is going to be 2 plus root 5, 2 minus root 5, 7/6. Somehow I don't know if this is going to work. Row reduced echelon form of B. No, it works fine. Divided by root 5. Oh, shush. That didn't help. Okay. Man, what the hell? I can't even think of what that's doing. I don't... That can't be a fraction, right? No. Alright, so this gets us that C1 is approximately 0.313661. C2 is approximately 0.686339. Yeah, well, okay. There's no dots if it's approximately. Okay, those values. So those get plugged back into our X up here. Okay, you'd want the exact values to actually be plugged in. So like figure out what the root is that's gonna get you, and you'll figure it out from there. All right, let's get out of here before ads hit again. So we're gonna go and find somebody. Math Fan Brian is not currently on. Dr. Gold's on, so we're going to go see Dr. Gold. He's currently in there and been in there for an hour and a half. Probably going to hang in for a little bit longer. I'd like to thank everybody for coming on over. Thank you, Phobos. And no, just Phobos for the raid. Thanks, Don, for heading on over after your game. And really, just thanks everybody for coming, hanging out. If anybody's interested, again, GOtEL is there. Game on 2-End Lupus, run by Coca Confession, L Bell, and 8-Bit D. And there are many other people who are contributing to this during the month of May. We're halfway through the month, and we are more than halfway to the total goal of everybody. We, on this channel, have just had a couple of individual small donations, so if anybody's interested, you can go Tiltify at nSimplex Pachinko and GOtEL /GOtEL2025. So, hope to see you all a bit later. I'm going to be back on Friday for gaming type stuff, and then next Monday for math stuff. So we're going to do curriculum on Monday and actual calculations on Wednesday. But if anybody has any calculations or whatever, come in any day you want. So I'll see you all later. My name's Obi-Wan Pez. This is nSimplex Pachinko. See you later.